Good evening, everyone. Thank you for coming out. I guess it's the autumnal equinox in the northern hemisphere, and I'm sure Santa Barbara has some crazy parties that you're giving up to listen to me talk. So what we're going to talk about today is where mass comes from, and I think we'll start with something that is familiar to everybody, which is an atom. About 100 years ago, two guys named Geiger and Marsden aimed a beam of alpha particles at a very thin gold foil with an apparatus looking something like that. Smashing an understood object into a less well understood object is basically all you need to know about experimental particle physics and nuclear physics. That's all my colleagues at Fermilab do. And they found something that was surprising to them. They thought that these alpha particles would sort of get stuck, but most of them sailed all the way through. But some of them bounced at very sharp angles, and this was completely unexpected. It led their lab director, Ernest Rutherford, who is actually from New Zealand originally. He got on the $100 bill in New Zealand for all of his efforts as a physicist. He figured out what's going on inside an atom, and that is that there are some very light electrons to even out the charge. Then there's a lot of empty space. That's why most of the alpha particles sail through an atom. And there's something very heavy in the middle, which we now call the nucleus. And this led to the Rutherford model of the atom, which is pictured here. All of the images here, if you get the PDF file from KITP, has a link for something else. So there's a link to Encyclopedia Britannica on the Rutherford model, Wikipedia for the Geiger-Marsden experiment, Wikipedia on Rutherford if you click on the dollar bill. So lots of sort of Easter eggs like that if you want to play with my PDF file when you get home. So in this atomic nucleus, the density is 13 orders of magnitude larger than it is in an atom. So that means that 1 part in 10 to the 13 actually inside an atom has stuff in it, and that's why all of the mass is focused in that point. Now, there's a mind-boggling number. If you want to get some idea of how much it is, take the mass of 2 aircraft carriers and compress it down to the size of a grain of sand, like the sand things that stick on you when you're walking along the beach. That's how dense the atomic nucleus is. Further scattering experiments, I said that all my experimental colleagues do is to scatter one thing off of another, revealed that the nuclei is made of something else called protons and neutrons. And this is sort of high school level. I'm sure most of you are familiar with this. I want to introduce a word, nucleon, which means a proton or a neutron. These two things are very similar. They have a very similar mass. So for most of what I talk about today, it really is just the nucleon. One or the other, the distinction between the two of them will only be important towards the end. Now, we all know something about nuclear technology. Humankind has harnessed nuclear reactions called fission. This is a picture of a nuclear reactor, I think one of the ones that blew up. The energy mechanism in stars is called fusion. We're also trying to harness that for serving the energy needs of humankind. This is a design of a fusion reactor. So whereas this one blew up, this one doesn't even exist yet. But the thing that I want to impress upon you is that even though we think of these things as immensely energetic, immensely powerful, the most awful and awesome energy source known to us, the amount of energy in these things is actually puny on the subject of what we want to talk about. 1% of the energy inside nuclei is released when you fuse them, even less than that, 0.1% when you break them apart in fission. So that means that the origin of mass of atoms and everyday objects, and you and me and everything else in this room, has to lie somewhere beyond nuclear chemistry. And this is what we want to talk about. So this is just to have it all on one slide. Your mass comes from something inside the protons and neutrons. So to explain how this all works, I have to give you some more background on physics. This is sort of going to be now at an advanced undergraduate, beginning graduate student level, but I'll try to make it as simple as I can. So further scattering experiments revealed that the nucleons are made up of other particles called quarks, in particular the up quark and the down quark. And here's the electron. These are in the same color because they're sort of partners. And the electron has a partner called a neutrino. Neutrinos are a big deal at my laboratory these days, but we won't talk about them at all tonight. And then, for reasons we don't very well understand, this whole pattern, which is most of all we can see in the universe, is repeated a second time and a third time. And then there are various things called gauge bosons, which mediate forces between these two. So I have some pictures to make that a little bit clearer in a moment. And then there is another boson called a Higgs boson, discovered a couple years ago on July 4th. And it's a different color because it has some basic properties that are different than these. We don't have time to talk about all these things. We'll really just be talking about the up and down quarks, the electron I already mentioned, and then one of the gauge bosons over here called the gluon. One thing you'll notice when you listen to someone like me talk is that any piece of physics terminology that was introduced until, say, 1962 sounds very serious, and then anything from the mid-60s on sounds goofy. So, quarks, gluons, charm, strange, top, you can guess which ones are founded after all the turmoil of the early 60s. Actually, my research has more to do with these quarks, and we also won't have time to do that, but that's something that we talked about an awful lot for the past 8 weeks. Okay, so you have these quarks and these gluons, and they make two kinds of particles, and so we always have this taxonomy. It's almost as bad as botany. We call them hadrons. And then there's one called baryons. Bary is Greek for kind of massive. And so the proton and the neutron are both baryons. A proton is made of 2 up quarks and a down quark. A neutron is made of 1 up quark and 2 down quarks. So I said they're very similar. Now you see exactly what the difference is. But there are lots and lots of other baryons. So there's one called a delta, which looks like it's made of the same stuff as the proton, but the way the quarks are arranged on the inside is a bit different. So it's a different particle. And they have completely different names because when they are first discovered, no one knew that they had anything to do with each other. Then there is something called a lambda baryon. You replace a down quark with a strange quark. And something that has a Greek letter that no one can remember, so everyone calls it a cascade. Then there are particles that are made up of a quark and an antiquark, and those are called mesons. So the me in meson is the same as the me in medium. This means things that are sort of medium massive. And so we put a bar over a quark when we mean an antiquark. So it's an anti-U and a down, and one configuration of spin makes a pion. Change the spins, you get a row, and then all these other more exotic quarks that I like to study make other kinds of mesons. And so quarks were originally introduced to make sense out of this large number of mesons and baryons. There seemed to be too many of them to be anything fundamental. There are also, I said, our experimental colleagues do nothing but smash stuff together. There are more scattering experiments that also revealed a structure. And this was not understood back in the 60s, so they're given a different name, partons. Very imaginative, right? The electron scatters off a part of the nucleon. What are you going to call that part? You call it a parton. Dueling professors at Caltech, and these aces were due to a postdoc at Caltech who couldn't get his paper published. Now, I'm going to jump ahead a little bit just to get your mind focused on what the real problem is. The quark masses. So we have an idea of what the mass of these quarks are. And we measure them in a unit called MeV divided by c squared. C is the speed of light, so we sort of use Einsteinian units. What's an MeV? An MeV is 1,000,000 electron volts. You know what 1,000,000 means. An electron volt is the energy an electron gains when you go from through a potential of 1 volt. So the way I like to explain this to students is that when I was a kid, I had a long bus ride home. We didn't have iPods and stuff like that, but we did have transistor radios. And when we were really bored, we would take out the 9-volt battery, the same kind of batteries you use these days for smoke detectors. And we would touch our tongue to the 2 terminals. You shouldn't try it, believe me, it's sort of weird. But that's a 9-volt battery, so every electron in our saliva would gain 9 electron volts. So instead of 9 electron volts, 2 ups and a down give 9 million electron volts worth of energy. And the only thing you really need to understand from all these equations is that 9.4 is a lot less than 940. If you switch to a neutron, the down quark mass is a little bit larger than the up quark mass. We'll get back to that. Still, 12 is a lot less than 940. The lightest of all these hadrons is called the pion. It just has an up and a down quark, and even in that case, 7 is a lot less than 140. So something else has to create all of the additional mass. Okay, so now a little advanced undergraduate physics. Electrons and everything else in the chart are simultaneously particles and waves. Often in the press they say there's sometimes this and sometimes that, but they are actually both things all the time. And the best way to see this is in this so-called double slit experiment. So if you shine a beam of any of this stuff I've been talking about and send it through 2 slits, you can make the beam so that it's so weak that if you think of it as a particle, there's only one near the slit at any given time. But even so, it accumulates in this pattern, which is characteristic of a wave. Okay, I don't want to go into this in too much detail. The main point is that we have a mathematical concept which is ideally suited to treating a phenomenon like this. So physicists are thought to have their heads in the clouds, but we're actually very practical people. I don't want to debate the philosophy of which it is and why. What I want is a mathematical tool that enables me to understand it. And that tool is called quantum field theory. And what it means is that every one of those things on the chart is assigned something called a quantum field. Quantum, because quantum mechanics is at the root of an experiment like this. And a field means that every one of them has a few numbers describing it, but one number for every point in space and for every instant in time. And then a very beautiful and, for my purpose, convenient way of understanding all of quantum mechanics is that what these fields do is they explore every possible way of moving with a tendency to follow the path that you would have in classical physics. And it's by exploring everything around them that they can know that there are 2 slits and be both particles and waves at the same time. So when I get to talking about real calculations, we are using these quantum fields all the time. The next thing I would like to explain is how we view forces. I mentioned that there were these gauge bosons. Those were the things in the sort of salmon that's a day old color. And if you exchange a boson from one, say, electron to another, you can get a picture like this. So this is an electron. This is, say, a positron. So the arrow is reversed. The positron is an antiparticle of an electron. And an atom is held together by exchanging photons. And the photon feels the electric charge of these things. So the pull or push is proportional to the charge of these different particles it might interact with. Now, is there anyone in the audience who can tell me the difference between this diagram and this diagram? Okay, so if you're colorblind, you have an excuse. What do you think is the difference?
One's pretty looking, and one's a little bit dull looking.
Okay, well, so actually I would say this one is colorful. And the reason it is in color is that the quarks have a property that has some analogy with electric charge, but we call it color, and I will explain why we call it color. And they're held together by these gluons. Remember I said the gluon with the silly name was going to be important. And the remarkable thing about gluons is that unlike a photon, which has no electric charge, the gluon also carries color. In fact, it carries color and anticolor. So we have red, blue, and green are the colors of the quarks. Cyan, yellow, and magenta are the colors of the antiquarks. So this is, for example, a very primitive picture of how a meson is held together. The laws of physics behind these are dictated by symmetries, which are something we physicists think are very beautiful. I will explain what a U1 symmetry is on the next slide, and also an SU3 symmetry. There is a difference between the two of them. If you insist that the equations reproduce this symmetry, it's very constraining. You can't have any arbitrary kind of interaction. It's very constraining what happens here, and it is the secret behind how all of these things work. Okay, so U1 is just like rotating a circle. And so if you rotate a circle through any angle, it still looks the same, right? And I can rotate the angle through the circle through one angle and then through another angle, and it ends up being in the same place as if I reverse the order of the two rotations. Okay? Does that make sense? I see some people nodding their heads. Okay? So, this is almost trivial. Now, sometimes you can have rotations, like in 3 dimensions, and the order matters. So if you have a cube in 3 dimensions, and you rotate it about the x-axis and then the y-axis, it ends up in a different place than if you rotate in first about the y-axis and then the x-axis. Or as Greg Hoover said today, another example of operations don't commute are putting on your sock and your shoe. If you put your sock on after your shoe, it ends up in a different state. But I would say, first of all, that's not a symmetry. And I'm glad your wife has come back from St. Louis. She can help you get dressed in the morning. The reason I chose this Rubik's Cube is because it has these nice colors. And our SU3 symmetry group is kind of like the rotations in 3-dimensional space that we experience, although it is in some other more abstract sense. But the main difference is that if you add the same amount of red, the same amount of blue, and the same amount of green, you get something that is neutral. And that, in fact, is why we call it color, because if you add those different colors of light, like in the projector, you get white, right? This white space here has an equal amount of red, green, and blue light coming out of the projector, whereas the 3 sides of the Rubik's Cube do not. Now, I said that gluons carry color, and that means that the symmetry dictating the equation says that in addition to the interaction between the quarks and the gluons can interact with each other. And if you stare at this long enough, you'll see that I got all of the primary and anti-primary colors matched up right. And then, of course, this is quantum mechanics. In quantum mechanics, crazy things can happen. So here's the quark and a meson, the anti-quark. The gluon comes out. Because of this interaction, the gluon can split into different colored gluons and then rejoin. This is a quantum mechanical correction to the force. You can also have a loop of quarks here. 40 years ago, when people were first thinking about it, it was really, really hard to figure out how to do the math. Right? There's actually an equation that corresponds to this picture and to this picture. And now this is something that every graduate student does. But 40 years ago, there were only 2 graduate students. And the professor of one of those students, Director Emeritus David Gross, who did this calculation, they got the Nobel Prize for doing this simple calculation first. And the thing is that this makes QCD, quantum chromodynamics, completely different from QED, quantum electrodynamics. So for some reason, we call this quantum chromodynamics instead of color dynamics. That's just one of our affectations. And so when they did this calculation, they discovered that the force between here, there's always a geometric factor that goes like 1 over r squared. So in electrodynamics, there's just some coupling strength divided by r squared. Same with gravity, actually. But instead of the coupling strength, they got this function that depends on r. And what they really had to calculate was this number, which we call beta 0, and they had to figure out the sign of it. These guys got the Nobel Prize for figuring out whether this number is positive or negative. And you get right down to it. To balance the dimensions, this is a logarithm. I'm sure everybody here loves logarithms. You have to balance the dimensions. So this is not the same lambda as before. It is a new energy scale. It's a new energy scale that comes out of these quantum fluctuations. So there's a source of energy that comes just from quantum mechanics. Later, I will call this the running coupling and denote it as alpha S of R. Okay, I want to explore this a little bit more. So now we're going to start doing calculations live and in public, which is maybe not always a good idea. So quantum electrodynamics, the idea is that you have an electron and a positron, or a negative charge and a positive charge, and you pull them apart. And actually, I'm pulling them apart vertically. And if you stare at this, you will see some field lines for the electric field. You pull them a bit further, you get the same kind of picture, just everything blows up. That's what I meant by this 1 over r squared just being geometry. And if you make it even larger, the whole picture just blows up. In fact, if you have really sharp eyes, you'll know that I used presentation software to make this diagram and then just shrink the other two. Nevertheless, it is correct. And so when you do this, as you learn in high school, you get a force curve that looks something like this. So it goes to negative infinity at 0, and it goes to 0 as you spread things very far apart. Right? If you separate two planets, the gravitational force goes to 0 as you make infinite separation. You separate two charges, the force between them goes to 0 as you have infinite separation. Okay, so now we're going to do a calculation of the same thing for QCD. Okay, so this is a calculation, actually from one of the participants early in this program and a couple of his collaborators. And here, at short distances, there's just a small deviation. That was due to that formula on the previous slide. But at large distances, it flattens off. And so that means that no matter how far apart you pull a source of color and a source of anticolor, the force between them remains constant. And energy is force times distance, so you can build up a hell of a lot of energy as you pull these things apart. Actually, in the real world, when you get them far enough apart, there's enough energy to make two new quarks and antiquarks, so that the quark here pairs up with the antiquark here, and the quark here with the antiquark there. You get two mesons, and then you can just separate them as far as possible. But this means that the color never gets very far outside a source of color. This is called color confinement. And in fact, none of these objects that have color as one of its fundamental properties has ever been observed in the laboratory on its own. And this is because of the color confinement. So you can fit this lambda from the Gross-Wilczek-Politzer calculation comes back in here, and if you square this number, which is so something like half the proton mass, roughly speaking, it also gives the units of this force. And so when you were walking in, I had this video going. This video is from the computer solving the equations of QCD. These are the configurations of gluons in empty space. So when you leave, look up in the sky, look at an empty space. This kind of stuff is going on at microscopic scales inside the shortest distances. And when you have the sources of color and anticolor and pull them apart, you have to expel this so-called vacuum field. And here is, again, a computer calculation of that. So you have a red quark and I guess it's a cyan antiquark going back and forth. And if you stare at this, you see that when they come apart, there's actually a tube of the region where these vacuum gluons have been expelled, and it's about the same length. You know, once you get bigger than a sphere, it's about the same diameter in this tube, shaped kind of like a sausage. Now, this is for a meson. We're not made of mesons, we're made of nucleons, so of course we can do this also for nucleons. At this picnic with the famous soccer game, we had tri-tip, which was delicious, so that's where I got that silly idea. And so you see the same thing going on in the nucleons, which make up the nuclei at the center of atoms, which make up us. And I emphasize these three videos that look really cool, but unlike many things that look really cool, this is real science behind it. They are solving, in a way I'll tell you in a minute, the same kind of things that we've been having this workshop on for the past 8 weeks. Okay, so you have this sausage-shaped flux tube, and let me just summarize the end of this. So in quantum chromodynamics, quantum fluctuations produce a new dynamical energy scale, which we call with the Greek letter lambda. Everything stems from lambda and the symmetry. So actually, I could change this symmetry group. You can almost guess if the mathematicians use the letters S, U, and then 3 in parentheses, there's probably something that's S, U, and 4 in parentheses, 5, 6. You can change that. Actually, some of the people who've been participating in this program have varied this number, and you see things that are more or less the same. You still see this sausage-like object coming out. So this is important, and this energy scale is important. So for example, the running coupling that I mentioned turns to 1 at this distance, because then the logarithm is 0. The thickness of this sausage is proportional to 1 over lambda, and the nucleon mass is proportional to lambda. And all of the proportionality constants here, there'll be one thing for SU3 symmetry, something else for SU4 symmetry. Part of the reason why some of my colleagues in this program are changing the number of colors is because this is a very amazing phenomenon. We want to know whether nature makes use of it at other scales. So I didn't tell you where the quark masses came from. They come from somewhere else. That's something that we don't understand very well. And some of my friends think that a repeat of this QCD dynamics might have something to do with it. You can tell there are no Germans here because no one giggled. Okay, so I've been talking about calculating and I've been talking about computing. And so now I'm going to tell you how we actually calculate all these things. Briefly, and then I'll talk a little bit about the difference between protons and neutrons, and then we'll be done. So those videos, also those green points for the force that came across, they were all calculated with supercomputers. The reason we do this is that when you get to larger scales, so when the sausage develops, the gluonic interactions pile up in a nonlinear way. You can't do the calculation with pencil and paper anymore. So we have these basic equations. They're constrained by the SU3 symmetry that I told you about, and we teach a supercomputer how to solve them. Now, a problem is that I said that we've got a few numbers for every point in space and actually also in time, and that's an uncountably infinite number of things to keep track of. What does uncountably infinite mean? So you know the numbers 1, 2, 3, 4, 5, right? The counting numbers, some people call them. Anything that is as infinite as the counting numbers is called a countable infinity. But you know, there's a point in space and there's a point right next to it, and right next to it. It's much denser than the counting numbers, and so that infinity is called an uncountable infinity. And I know it sounds dumb to say, but you know, when you're doing a calculation, you have to know how to count. And if you have something uncountable, it is hard to count. Okay, so we have to do something that turns this problem from uncountable into countable. And what we do is say, okay, so I'm supposed to have a field for every point in, say, some three-dimensional cube, some cell like this. And so instead of treating all of them, let me just sort of average over everything and replace all of the, say, quark variables in this box by just 1. Okay, so that's what this picture is supposed to do. Miraculously, I don't know how people prepared talks before the age of Google and the internet. You enter a picture of a cube, and you get something that is already color-coded exactly the way I want it. I mean, it's just amazing. Okay, so you shrink the uncountable infinity of quark field in this cube into just 1 at a dot. Okay, so that's what I said there. Make it countable. And so then we have a whole bunch of these dots, and we put them in a regular array, which is called a lattice. People talk about lattices in condensed matter systems because the ions, say in a metal, are periodically spaced apart. Most people only know a lattice from the pattern of dough on top of a cherry pie, but except for the color, you can imagine this. The quark fields live on what we call the sites, so these dots, like on the previous transparency. I've been emphasizing this symmetry to teach the computer to handle the symmetry in the right way. You actually put the gluons on the links connecting the sites. Okay? Then you have as many as you can have in the x direction, so left and right. Then as many back and forth, y, as many up and down, z, and then twice as many in the time direction. This 4 stands for the time direction. All of the equations are compatible with Einstein's special relativity, so we don't treat time and space any different. Okay, now we want to, this lattice is the thing why our program is called lattice gauge theory for the LHC and beyond. It's people using this kind of setup to solve related physics problems. And we want to put it on a computer, so we also have to make the volume finite, because then you have a finite number of things to keep track of. And so obviously the volume that is in our computer is smaller than that of the universe, but we don't usually have to worry about the boundary conditions at the edge of the universe to get on with everyday life, so it's the same thing here. That's okay. But we do have to make the size of this larger than the typical scale of this sausage-like object that's causing the energy of the hadrons. So I said before that in quantum mechanics, these fields have to explore all the possible paths, so that's the program you write. You reduce it to this finite system that I just tried to explain, and you teach the computer how to solve the equations. It's not quite as simple as that, but we have pretty smart guys, including people and gals. I see you, Marina. And so we've learned how to program the computer to do this. Actually, if you go to one of our conferences, there's a lot of agreement on the physics, but lots of arguments about, well, why did you implement this step this way? And the sort of things that experts can tend to get into. So when we do these things, we have some of the largest computer jobs that are done by anyone who is not a spook. And we use some of the biggest computers. The jargon for this in the computer world is high capability. So it's a computer capable of doing the largest computing problem at any given time. So we make heavy usage of those. After that is done, we generate, if you like, data describing quantum chromodynamics with these computers. Then we have to analyze this data to get out physics results that could be compared to experiment or put into the animation or drawn on a graph. And these are tens of thousands, maybe hundreds of thousands of medium-sized jobs. So medium-sized means more than you could carry out just on your laptop. So at the national labs, the example shown here is from my lab, Fermilab. We built high-capacity clusters. So this is like going down to the computer store, buying 500 high-end desktop computers, throwing out the monitors, and hooking them up together so that you can run all these jobs. So that's a picture of one of those. Now, the information I showed you so far has been qualitative or semi-quantitative. And physicists actually really like to get quantitative. You know, we make pretty pictures to please the public. But what really makes us excited is that when we can calculate something precisely and see whether it agrees with a well-accepted experiment. What we like even better is when we are confident that we can calculate something accurately and we compare it to a brand new experiment and find that they disagree, because that's a sign that our theory of all the experiments is incomplete, and that would be the most exciting thing. So, can we calculate many of these hadron masses, right? I told you that there are many different hadrons, many different baryons, many different mesons, and do they agree with the lab measurements that go back to the 50s and 60s? So here's a summary from a review article I wrote a couple years ago. And what you have is, for example, a black line. That's what's measured in experiment. And then you have a bunch of dots. These are things that people from all of these different collaborations. Let's see. We have some of the BMW group in the audience. We have some of the RBC group in the audience. Some of the Milk. We had people from UK QCD and PAC CS here. I don't know that the other guys showed up. So what you see is that for the pion and the rho, it works fine. Here is the nucleon, the thing that makes up most of us. It works out fine. And all across the board for all of these things with different so-called flavors of quarks inside them. So the nice thing about this is that it agrees very well with the measurements. We use supercomputers. Anything on a big computer is a bit of a black box. I think it's also comforting to know that if this group, that group, and the other group, the people who argue about the details when they sit around with each other, in the end, all agree very well. So, in the 5 or so minutes that remain, I would like to get back to the difference between the proton and the neutron. So remember, the proton has 2 ups and a down, and the neutron has 2 downs and an up. Since we're doing this in a computer, we can change what the inputs are, and we can ask questions like, what would happen if the electron mass changed? What would happen if the up and down quark masses changed? What happens if the strength of electromagnetism changes? Now, one difference between the proton and the neutron that I didn't tell you about yet, you probably know, the proton is charged. That means that the total charge of the 2 ups and the down adds up to 1, whereas the total charge of the 2 downs and an up adds up to 0. That means in a proton, there are electromagnetic forces that tend to push it out and generate some extra energy, and that extra energy is an extra little bit of mass. And that energy in the electromagnetism is comparable to the difference between these 2 masses. So there's a competition between electromagnetism trying to make the proton a bit more massive than the neutron, and the extra mass of the down quark trying to make the neutron more massive. This is actually a big deal, because if a proton were more massive than a neutron, then a proton would decay into a positron, a neutron, and a neutrino. The positrons would find the electrons, and all you would have left in the universe would be neutron stars and neutrinos. Okay, so the fact that it worked out the way it worked out actually makes a big deal for complicated things like biological systems. Right, we're all biological systems. Okay, so in our universe, to 1 digit, the electron mass is half an MeV. I've dropped the c-squareds. The up quark mass is 2.3. M down is 4.7. And the difference is 1.3. So you see these numbers are all not hugely different. So here's a plot from my friends Laurent Lelouch, who is back there somewhere, and Zoltan Fodor, who is sitting next to that piece of wood in the middle. And so they have undertaken with their collaborators the first serious calculation in quantum chromodynamics of the mass difference of the proton and the neutron. And they get it right. Okay, so that's good. But then they go a bit further and try to address these questions I had on the last slide of what happens when you change the parameters. So let me try to explain what we have here. So alpha is the strength of electromagnetism, and it's divided by what it is in the real world. So if the x-axis is 1, that's the real world. This turns electromagnetism off, and this doubles its strength. On the y-axis, we have the difference in the quark masses, because one is 2 ups and a down, and the other is 2 downs and an up. It's really the difference between up and down that's going to change the mass. Again, divided by what it is in the real world, the physical world. So again, then on the y-axis, you want to go to the point it's 1. So we live here, and we had on the previous slide that the mass difference was about 1.3, 1.4. And these lines show make electromagnetism stronger or weaker, can be compensated by changing as a knob in your computer program the difference between the down and up quark masses. This has a 1 MeV difference. This is a 2 MeV difference. So if you make this difference larger and larger, the mass difference will go up and be the same. But what's interesting is when you get down to this level, where the mass difference between a proton and neutron would be half an MeV or less. This is their label, inverse beta decay. It's a bit of jargon. It happens when the mass of the neutron is less than the proton plus the electron. What happens is that you would make hydrogen, say at the appropriate time in the universe, and then the electron every now and then would sort of get close to the center of the proton, and the proton would basically eat the electron, turn into a neutron, and spit out a neutrino. So this would be another reaction that would change the way the universe ends up being, because there wouldn't be any hydrogen left. Hydrogen would go away. Helium would probably exist. But then if you go to all the other elements, which nuclei are stable and which aren't, it would change completely. You probably could spend days trying to figure out which ones would change depending on where you are in this blue region. And finally, when you get to the point where they're equal, so the very lower part here, this is when even a free proton will decay into a positron, a neutron, and neutrino. That was that very bleak world that I told you about. So I think the takeaway from this are twofold. And the qualitative thing, the universe is not so very far away. The universe that we know and love is not so far away from some worlds that are really, really creepy. So that's sort of the human aspect. The scientific aspect is that we've come far enough to understand this in enough detail that these are not just pretty pictures that someone could sketch on a blackboard. This is quantitative, coming from detailed calculations that are carried out with a lot of care and a lot of passion. So, in the blue region, biochemistry, other things as we know it, is impossible. Okay, so I'm doing okay. Greg said to do 45 to 50 minutes, so there's time for questions. The origin of everyday mass. Quantum chromodynamics had a reductionist origin. It came from doing these scattering experiments and trying to make sense of the botany of all the different hadrons. And in the end, we realized that they were made of quarks and gluons. What makes it fascinating these days is that various phenomena emerge from it. So instead of boring in and saying what's at the smallest scale, how much control do we have over these interactions that become really, really complicated as you get to larger distances? So out of the gluon-gluon interaction, this force arises. This force is associated with an energy scale. These things are generated by quantum mechanics. And this energy scale from quantum mechanics is the origin of the mass of everyday objects, including you and me. So Einstein said, actually, m equals E over c squared, and everybody since then has been rewriting the equation with the c squared on the other side. But this is the way this really works. The mass is the energy coming out of these sausage shaped things in QCD divided by c squared. We do these calculations not just for calculating the masses of these hadrons that have been seen in the laboratory for decades. Here, Yannick, my co-coordinator, made this nice drawing for our logo. The practitioners who've been at this workshop are interested in a whole host of other questions, and we use the same tool that I told you about today to attack these problems. So what are the properties of hadrons with more exotic quarks, the ones I said I study, like the charmed quark or the bottom quark? What we really want to see is deviations between lab measurements. So there are experiments going on. There was one at SLAC in Stanford, California that was shut down a few years ago, but there's a sort of successor in Japan. There's an ongoing experiment with a different technique to study these things at the Large Hadron Collider in Geneva. And what we really hope is that we can calculate certain reaction rates precisely enough, and they can measure them precisely enough. And then with confidence, we can see a discrepancy that we're willing to bet money on, because that would mean that we have discovered something new that we didn't know about before. And some of these things aren't trivial. The universe has a preponderance of matter over antimatter, even though we think at the very earliest stages they were equal. That means that some reactions of elementary particles have to go more in one direction than in the other. And we hope by us calculating these reaction rates and they measuring these reaction rates, we can unravel a new source for this kind of matter-antimatter generating interaction. There are other questions. If you heat up all these hadrons, you get something that astrophysicists like to call the primordial soup. It's where all the hadrons jumble up and the quarks and gluons are almost free. This is a very weird thing that's also studied in experiments, so we will have a talk tomorrow on this subject. The primordial soup is a liquid at high temperatures, and it cools into a gas, which is not at all the thing you usually think of when you cool a liquid. So it's very, very bizarre. It's a frontier science problem. I could go on and on for this. In fact, we could have had a whole week of lectures on things that we're trying to do. In fact, we had 8 weeks of lectures aimed at us, but we could have also filled a whole week in talks at this level on all the things we do. And so I'd like to thank the KITP for hosting our program. The animations are done by a guy named Derek Lineweaver in Adelaide, Australia. So I'd like to acknowledge the work that he's done in making it public so that people like me can use it in things like this. And I'd like to thank you and your mass for your attention.
Questions?
Thank you very much. This is on the KITP website, this presentation, or
it will be.
It will be. Oh,
yeah.
Great, good, cool.
Yeah, you can watch this every night.
Yeah. Well, anyway, so you've accounted for the mass of the hadrons.
Yeah.
What about the mass of the electron?
So the mass of the electron.
And what exactly is charge in that case?
So these three small numbers all have the same origin, and they come from the electron field, or the up quark field, or the down quark field interacting with the Higgs boson. So I don't know, it's not that late. I have some backup slides. Except you have to endure the silly animations, which are always... Okay, so the Higgs boson was discovered a couple years ago. Here's a bad joke about the Higgs boson. Okay, so the Higgs field behind the Higgs boson has some non-zero value everywhere in space. So that means it's something that anything that interacts with it has to sort of slog through. And the best analogy for this slogging through is to imagine different beings traversing a snowfield. So if you're on well-waxed skis, you can move across a snowfield very quickly, and that is equivalent to having a small mass. And this is what happens to the electron. The electron has a very small interaction with the Higgs field, so it can move very quickly through it. And if you like, there's some law that says that the, something like the mass times the velocity is going to be the same for all of them. Okay? So the electron mass comes from the interaction with the Higgs field. Yeah.
He's saying you've kicked the can down the road. You haven't answered the question.
So we have to add a little bit of relativity to get out of the tautology. In special relativity, one postulates that there is a maximum speed limit called the speed of light, because it turns out that light goes at that speed. And anything that goes at the speed of light cannot have a mass. It can have energy, but it can't have mass. And so without this interaction between the electron and the Higgs field, the electron would have no mass. But it bounces off, so it slows down and goes slower than the speed of light. And that in relativity is the same as having a mass. And then there are other particles that have a larger coupling to the Higgs field. They have a larger mass of this type.
Okay. Yes, you talk quite a bit about particles and fields, and we know quite a lot about what fields do, but do you have any explanation about what fields are? I mean, how do they interact at a distance? What is this thing?
Yeah. So we know a lot about fields. So the first thing that we know, and we know this from painstaking experiments compared to calculations. So this is not speculative at all, that fields do not interact at a distance. They interact locally. And anything that looks like it's an interaction at a distance comes because some other field has had some ripple going through it from one point to another, just like in those diagrams that I had earlier in the talk.
It's not an explanation of what the field
what is it? So to a practical person like me, a field is a handful of numbers for every point in space and time, and is because of the role of mathematics, it's a little bit difficult to convey the mechanism without using mathematics. That's why we try to rely on these pictures. What is true is that if you go out onto the beach and you see a water wave, it's very tangible because you can feel the water. You can feel it, you wade in, you can feel it going up above your knees and then back down again, and there's that weird sensation when it first hits the swimsuit. And you're right, none of these things are tangible the way that is, but I think that has more to do with the fact that we're talking about how things interact at distances that are just so damn tiny on the scale of human experience, right? 13 orders of magnitude from the size of an atom, which we can barely get our head around, to the size of the nucleus. Then the nucleus is made of these things that are even smaller, and then buried down inside of that is where all of these field interactions take place.
Is it like fields are a bunch of particles, or is it like they call it fabric? I won't say either.
Yeah, I don't want to say either. So I tried to say that these things are these objects we detect in the laboratory, like the electron, it's not like a particle and it's not like a wave. It is both of them simultaneously all the time. What is an object that can describe something like that. It's a field. And one example of a field is the surface of the water moving up and down. And you know that there are things that really look like big waves. But have another example of a wave would be on a string, right? You can get something that looks like a pulse. And so this is why all of this thing works out mathematically. But I personally don't like to spend too much time saying, what is it really? We can calculate. We have an understanding of these things mathematically, and we can calculate, and we can do it very accurately.
Okay. Because the mass of particles will change closer to the speed of light, is it safe to assume that the interactions of the hadrons will also change near the speed of light?
So yes and no. So these changes that you described are what we would call kinematic. They just have to do with motion. And the real question is whether the dynamic part of the interaction changes. And no, that's the same. It's part of what was behind when I said that everything we're doing is consistent with relativity. That means that everything behaves in exactly the way it has to behave, consistent with special relativity. But that's another lecture. There's a lecture on special relativity by Shankar from Yale, which is actually very good. So.
And it's already online because it's already happened.
Yeah.
The heat is getting everybody down. We got one. You got somebody, Craig? Yeah.
Thanks a lot for coming tonight. I really appreciate the lecture. So here's my question for you. First law of thermodynamics, its relationship with virtual particles, and how that, in essence, actualizes this physical universe, and in particular, the maintenance of or the origin of mass. Does that make sense?
Yeah, parts of it. Let's see if I got it right. So the first law of thermodynamics is the same as the conservation of energy. And when you have virtual particles, so I drew these diagrams, say where the gluon comes down and it splits into two others. Those are what we call virtual particles, and it's really actually a bit of a point of view. You can do all the calculations in a way that energy is always conserved, even with all of these quantum fluctuations. But there's a much more elegant, easier way to do it, in which you, during the calculation, allow very brief violations of the conservation of energy, even though, by the time you get from the initial state to the final state, everything is fine with conservation of energy.
So the assumption is we're living in a closed system. That's the modeling. But in essence, with virtual particles or quantum fluctuations, we see that the system, in essence, maybe for modeling purposes, yes, it's closed, but for all practical purposes, the system is open.
So the conservation of energy actually follows from assuming that the laws of physics are the same for all time, that they don't change with time. That's where it comes from. That, of course, is an assumption and it has to be tested by observations, but all observations are consistent with that.
Okay, but the virtual particles don't
Let's see if
violate
there's
that?
a different. Let's move on and see if there's another question. Yeah.
Does it bother you? It bothers me that quarks can have fractional charge. If an electron's an elementary particle and it's got a charge of 1, how can you have 2/3 charge or 1/3 charge?
Well, how can you have it? So nature says they got it, right? And, you got to live with what Mother Nature tells you. But this didn't really come up in the talk, but since you mentioned it, So for people who can't see because of the screen, I'm writing P equals UUD to remind you. So the charges add up 2/3 plus 2/3 minus 1/3. So the thing that actually gets out beyond this length scale characteristic of confinement has charge 1. And that is the thing that blows our minds, that all really works out that way.
Go ahead.
Hi. If this is a nonsense question, just say so. But are we just lucky that the universe doesn't operate in that blue section, for example? Or is it inevitable? Or maybe this is more of a philosophy question than a science question. But, you know, if it didn't, we wouldn't be here, so we wouldn't be talking about it. I'm just curious if you have an opinion about why it works.
Right. So this institute, if I may say so, is notorious for having programs by people called string theorists. And string theorists like to speculate on all nature, that sort of stuff. And so when I was a graduate student, which was 30 years ago, string theorists thought they were going to solve everything in 6 months. So in the meantime, they revised their ambitions, and so now they actually talk very seriously about something close to what you said, and that is that part of the universe could have slightly different quark and electron masses, like in the blue region, and then in such a part of the universe, life would never arise. And then there are other parts where the conditions are right so that life can arise and we can have this conversation. It's called the anthropic principle. It's scorned by a lot of other scientists because these different regions with these different parameters are so disconnected from each other, we could never communicate, we could never test this idea. So, you know, is that a scientific idea if you can't test it? So, I think the short answer is yes. We're lucky that we're not in the blue region.
All right, on that note, let's thank Andreas. So we should have some cool refreshments, cookies, etc., over by the courtyard. So if you just want to exit that way, or if you don't want to, you're just free to go.